In this video, we'll derive the isentropic efficiency relationship for nozzles using the first law of thermodynamics. So in this case, we're still doing isentropic efficiency, but we're looking at a nozzle. So a nozzle's function is to accelerate the fluid. So it doesn't produce any work. We're going to look at adiabatic nozzles. So it's going to change the velocity of the fluid by changing the cross-sectional area. So we're looking at isentropic efficiency. So again, we're starting at the same state 1 for both the adiabatic and isentropic. But when we try to go to state 2, for the isentropic, it's going to be different than than the adiabatic. We're going to look at isentropic. We're going to assume that this is an ideal isentropic process. But we're also going to assume then that the pressures are going to be the same as the state 2 pressure from the actual. With those two bits of information, we can get the other properties, and then we compare the actual to the isentropic. So let's look at the nozzle efficiency. Again, we're using the first law of thermodynamics, one inlet, one exit. It's on your reference data card under the open system. So in this case, it's adiabatic, so it's going to have no heat transfer. It's also got no work, because it's just a nozzle. It's nothing. There's no shafts coming in there. Now the velocity is going to change, so we can't say that the kinetic energy is negligible, but we can say the potential energy is negligible because it's we're not going to have a huge elevation shift. So now we're just left with our enthalpy terms and our velocity terms. Well, we can rewrite this equation in terms of velocity at state 2 to be equal to the velocity at state 2 squared over 2 is equal to the velocity at state 1 squared over 2 plus enthalpy at state 1 minus enthalpy at state 2. The reason we put it in terms of velocity at state 2 is because that's what we're trying to do. We're trying to accelerate our fluid, so we want to get a higher velocity at state 2. So now if we compare our ideal to our actual, so ideally we would get all of that energy would be that we had coming in. We're going to convert it all. We're going to get the max amount of velocity coming out, but in actuality we're going to have some irreversibilities. So we're not going to get as fast. So our actual is going to be less than our ideal in terms of velocity. So we'll have actual on top and our ideal velocity at state 2 on the bottom. We can add those over here. We can rewrite the in terms of the form of the equation we had above. Velocity 1 squared over 2 plus enthalpy at state 1 minus enthalpy at state 2, all divided by velocity at 1 at state squared over 2 plus enthalpy at state 1 minus enthalpy at state 2s. So the only difference here is this enthalpy at state 2s for the bottom part, because the initial states are the same for both. Now, if we were to assume, if you can make the assumption that the velocity at state 1 is negligible, that would mean that you'd have to have a pretty big nozzle change so that the velocity at state 1 is pretty small in comparison to the velocity at state 2. Then we can simplify it further to enthalpy 1 minus enthalpy 2 over the enthalpy 1 minus enthalpy 2s. Okay. That's equation. So 7.1 refers to the initial part here. We can only use this second part here if and only if the velocity at state 1 can be assumed to be negligible. Okay. So in general, use the first part. If you're told that the velocity at state 1 is negligible, you can use the second one.